Yeah, welcome to the talk about open standards and hardware integration. It's a bit of a workshop today, so I'll be doing some hands-on code things. So if you have any questions, just feel free to raise your hand or shout out, and we can discuss things. So it's supposed to be a bit interactive. Yeah, so I'm Thomas. I'm team lead of the embedded team at Auterion. So my team is basically the team that does most of the contributions in PX4. So you've seen at Marcus's talk before, there's 60%, and all these names, they're pretty much my team. Yeah, we do PX4. We mostly do upstream work, and quite a lot of the contributions and all the names that you would know are in my team. Today, we're looking in Pixhawk standards. So what can Pixhawk standards bring to you when you adopt them? What are they? What can they bring to you? And how do you properly use those? I'll give a quick overview in the beginning, and then we'll go through the most important standards, and I'll tell you what they can do for you. In the end, I'm going to look into a driver, a hands-on example where we see how drivers are made in PX4 and how you would add your own driver if you had a new hardware component and you would need a driver for it. We're going step by step through the code, and I'll tell you how to add a new driver. All right, does that sound right? Cool. All right, so let's get started with Pixhawk standards. Maybe you know, but PX4 can run on a lot of different drones. So here is 3 examples. There's a multicopter. This is a free-fly Astro. There's fixed-wing planes. For example, here the Albatross. We have VTOL planes, but we have all kinds of other airframes as well, or not even airframes, just vehicles. We have submarines, we have rovers, we have all kinds of mobile robotics applications. And when you look at these aircraft, you would think they're very different, right? There's no way the same software can drive all of those. And you would think, well, the avionics are probably quite different as well. And the hardware certainly is. So one has wings, the other one has propellers, but you would think the avionics are probably quite different as well. But when you look into the avionics, they're actually surprisingly similar. So if you build any vehicle, you would probably end up with the same set of avionics hardware components that you would put into the drone. So up here, you can see the pointer, right? Yeah, you can. So up here, we have sort of the core flight control inner loop kind of thing. So you would have accelerometers, you have barometric pressure sensors, you would add mags, so compasses, gyroscopes. You probably want some sort of persistent storage for parameters, that sort of. So you would have an EEPROM, flash memory, basically. You would want an SD card to store the logs. You would have external sensors, so sensors that you can't really put in your avionics bay that you would need to put somewhere on the external of the frame because they need airspeed, like so you need air coming in. So you would have an airspeed sensor that you connect with a cable. You have a GPS sensor, LiDAR distance sensor. You'd have motors connected to ESCs. And if you go fancy, you might have a mission computer with object avoidance, cameras, and some payload. So you're just flying drones for fun, you probably want to add a camera or any other kind of payload underneath. And then, of course, you want radio control, being it a data link for telemetry or actual RC control, you want probably some sort of radio control. So any of these drones have pretty much all of these components. So the multicopters are mostly missing an airspeed sensor. You can find perfectly fine without the LiDAR sensor. But I mean, typically, these things don't really change that much between the different airframes. Yeah, so let's exploit this similarity, right? I mean, why invent everything from scratch if you can just use the same thing for all the different vehicles? And this is exactly what the standards are made for. Just they'd say if you use the standard, you'll have something that works, and it's the same thing for every vehicle. If you look at the Pixhawk standards and where they fit into this exactly the same picture, we can see these red bars that I added here, and they tell you which Pixhawk standard applies to the different areas in this picture. So I'm going to talk about all of them, basically. So one of the newer ones, and probably the easiest to understand ones, are the Pixhawk Payload bus and the Pixhawk radio interface standard. So the Pixhawk Payload bus is, for example, a standard that standardizes the interface underneath the drone where you plug in the payload. And when you adopt that, you can accept multiple payloads from different vendors, and you can just plug them in, and they should just work. The same for the ground station is the Pixhawk radio interface standard. So there's multiple radio links available, multiple protocols from multiple vendors. But the GCS really is this tablet thing, right? And if you want to control different drones, you probably want to add a different radio link module. And this radio interface standard is really the standard for this radio bay in the ground control unit. So you can interchange the different radio modules. Other standards, the Pixhawk Autopilot bus. This allows you to basically change the whole FMU flight control unit with another one. The connector standard, which is just really about the connectors to connect external devices to it. The Autopilot standard, which sort of is a wrap around all these different components here, and the Pixhawk Smart Battery standard for smart batteries, which is still in draft. Right, so let's get going. Let's get started with the Pixhawk connector standard. So that's the thing here, which is really the oldest standard in the Pixhawk standards family. And the Pixhawk connector standard really is about the white little connectors that you see on these on the different flight control units they can buy. So on the left is a Holybro Pixhawk 4, and on the right is the adapter board from Skynode. And you may have wondered how did they agree that they all use exactly the same connectors and you can just plug in everything? And that's really the Pixhawk connector standard that defines this. So it basically defines all the physical interfaces. So these JST, GH connectors, they're pretty good. They're reliable, and they have a mechanical lock-in. And it also defines the electrical connections within these connectors. So there's a standard for telemetry ports, which are serial ports, UART in the end. There's one for the GPS port, one for CAN, I2C, SPI, and debug ports. So this allows you to interchange external components. Yeah, go ahead.
Next slide. We've seen some modules now that have automotive Ethernet. Are they adopting that into the interconnect standard now?
Yeah, so there are some, exactly. So this is not part of the standard right now, but yeah, we could potentially standardize that. I think it's the Holybro, the one with the mission computer now, has Ethernet. Okay, yeah. It's not picked up yet, but that would definitely be something we should put in there as well, yeah. Absolutely right. Yeah, so what that gives you is that you can buy hardware from different vendors and you can just plug them in and it works because it's all defined and it's all the same thing. So for example, you can buy GPS modules from 3 different vendors and you can plug them into the GPS port on your flight controller and it should just work. And this does not just work. Oh, there we go. Cool. Right, so that was easy. Let's go with the Pixhawk Autopilot bus standard, which DSO 10. So this is this block here. Right. On a picture, it looks like this. So the Autopilot bus is basically the black connector here. So it's not the white ones, which is the Pixhawk connector standard, but it's this black high-density connector here. And this one allows you to basically buy this unit here, which contains the FMU as well as a sensor set, a standardized sensor set as one block, but build your own baseboard. So you can build for your drone, you can build your own baseboard for a deep, tight integration of the whole electronics. And then just buy an off-the-shelf Pixhawk Autopilot bus compatible flight controller, and you can just plug it in. And if you did everything right, that should just work. There's more examples. For example, also the Skynode is actually Pixhawk Autopilot bus compatible. So when you open up the Skynode, then you see this part here. So this unit here is actually just a plugged-in module that is compliant with Pixhawk Autopilot bus. So you could theoretically open up a Sky node and plug in this piece here from Holybro in, and it should just work because it's the same standard. For Auterion, so we sell the Sky node, and for us, it's what we want vendors to do is actually to take the reference design of Sky node, put that into the baseboard of their drone, and then just plug in an FMU V5X, FMU V6X compatible Autopilot onto that baseboard. So this is really what this Pixhawk Autopilot bus gives you. Yeah, so maybe you've seen at Holybro's booth out there, there's different modules, different autopilots you can buy. So there's one, for example, from NXP they have now. There's FMU V6, which is the STM32H7, and so on, right? So that's really about that. Yeah, so it's electrical interface. So all the pins are defined. The pinouts for those two connectors are well defined in there. And also the mechanical layout on how this whole thing should look like. And it's really, this is the premise of this. So you can build a baseboard that can accept any FMU V5X, any FMU V6X, or even any other autopilot that follows the same pinout, and you can just accept those onto your baseboard. This also makes it easier for you to upgrade to new generations of flight controllers without having to redo your own baseboard. Yeah, so with that, we go straight into the actual standards for the autopilots. So we've talked about the connector now. This is the connector. Now, for the autopilot themselves, there's also standards. Now, the standard here is really about mechanical and electrical compatibility. But the Pixhawk Autopilot standard is really about software compatibility, right? So you can have the pinout and the connectors well defined, but it doesn't mean that the software will actually run on this, because the software then runs on the actual components and the actual drivers, on the actual sensors that you have on the autopilot. So I'm just going to talk about the two newest ones, so FMU V5X, FMU V6X, which are the two newest autopilot standards in the Pixhawk family. And they're basically this piece here. So they're mostly everything that is on top of the Pixhawk Autopilot bus, but some of them also include this I/O processor, which we can talk about later. But I mean, it's mostly this part above the Autopilot bus. Yeah, they define a set of hardware components that are inside an autopilot. So they say, you're going to use this processor, you're going to use this accelerometer, this gyroscope, this barometric pressure sensor, and this EEPROM chip, and they're going to be connected this way to the processor, and then you're following the standard. By doing that, you ensure that it's compatible with PX4 out of the box, right? Because PX4, you can just do make PX4 FMU V5X, and that assumes a certain set of sensors to be present. It assumes the sensors to be present on certain buses. And if you follow the same design, you don't have to modify PX4, and you're just immediately compatible with PX4. That's what this is all about. It's all about software compatibility here. Yeah, so as I said, there's V5X and V6X. The main difference between those is the processor. So V5X is based on the STM32F7, and the V6X is based on the STM32H7. Other than that, they're pretty much identical. The H7 has a much higher processor speed and has more memory, and is a bit more modern design. But yeah, apart from that, they're fairly identical. Yeah, so this is what it's all about. You can just check out open source PX4. You type in make PX4 FMU V5X upload, and you're good. And you don't have to do any software changes, and it immediately runs. If you go and change your gyroscope as another one, you probably will need to write the driver for that. You will need to make your own board config. You need to do all of that to stay compatible. And you'll need to carry that forward into all the updates you're going to do to PX4. So following the standard really saves you work here. Then next up, Pixhawk Payload bus standard. This is down here. So this is a picture from Gramsci. This is the manufacturer of gimbals. And they built Pixhawk Payload bus standard compliant gimbals. And it's basically a definition of the mechanical interface here. And so this was contributed by FreeFly, I think, and Gramsci. And it defines the mechanical interface and the electrical interface here. So you can get a CAD file of this. You can get the whole definition of all the pins for the connector. And it provides interfaces for USB, Ethernet, CAN, UART, etc. Right? So you can build a payload that uses Ethernet and communicates over Ethernet with the rest of the drone. And yeah, you can build that such that it's compatible with any drone that offers a payload bay that is compliant with the standard. Yeah, so this is more a conceptual design again. So you would have your own carrier baseboard here, and then towards the top, you add the Pixhawk Autopilot bus to accept an autopilot, so the FMU. And towards the bottom, you would adopt the Pixhawk Payload bus, and then you can accept any payload. Maybe as a note, the Pixhawk Payload bus is all about hardware compatibility. It's not really about software. So, I mean, it doesn't mean that when you build any random device that uses Ethernet and you can plug it in and it's electrically compatible, it doesn't mean that there's suddenly a driver that makes it do interesting things. So depending on the kind of thing that you build, it doesn't ensure software compatibility, of course. If you build a gimbal that is MAVLink compliant, for example, then yes, you will have software compatibility immediately as well. Then, yeah, as the last one, the newest standard, the Pixhawk radio interface standard. So I'm just going to quickly go into this one. So this is down here, and it basically defines a interface connector where you can swap out radio modules on your ground station. So you can plug in other radio modules to control different drones with the same ground station. So if you're a ground station vendor, adopting that allows your ground station to be used more widely. If you're a radio vendor, adopting that allows you to use your radio on more ground stations. It's that easy. Cool. Yeah, so now we've seen a lot of standards, but you might be asking yourself, what does it bring? What's the value for me, right? Why should I care about standards? I have my own requirements. I need an FMU with a slightly better gyro, and so I'm just going to swap that out, and then I can save a few pins because I don't need this, so I can just take that out as well. So why should I care about these standards if I just build a product? And there are multiple reasons for this. So the first one we've talked about already is software compatibility. So you don't have to modify PX4 to make it run on your drone, which can save you, it saves you cost, it saves you effort, it saves you headaches, and it allows you to be compatible with always the newest version. So you don't have to have time, you don't have to reserve time to bring in the new features onto your own branch of the software to deploy it. We've seen a bit with Android, for example. So in Android, you can buy a Samsung phone, which runs Android, but it runs Samsung's little own customized version of Android. So when the new Android comes out, you wait for a year until you get the update because they need to pull down all their changes onto this Android release. Now, if you just stick to the hardware standards, then you don't need to do that. You can just run straight upstream and you're good to go. At the same time, the standard is by far the most used configuration of hardware out there. So if you use the standard set of sensors and the standard hardware components, you can benefit from all the testing that other companies have done. So there's a lot of hobbyists and a lot of companies that fly V5X compliant flight controllers out there. And all the bugs they raise are probably going to be fixed by somebody else or even themselves that also fly FMU V5X compliant flight controllers. Now, if you have a completely different hardware set and there's some driver problems or something, you're probably not going to benefit from that. You're on your own, you have to fix them yourself. So that's something that is some value for you. And also just reduce development effort. So let's say you have the Pixhawk standard connector standard in your drone. You can buy external components from any vendor and you can just plug them in and it works. So you don't have to build everything from scratch. You don't have to build your own GPS modules. You don't have to build your own airspeed sensor modules. You can just get everything from vendors and plug it in. And it's also better for the vendors because the vendors can target a much wider customer base by building sensors that adopt the standard, right? So that's the ultimate open standard here. It's basically train tracks are defined to have a distance, or the standard distance between train tracks is 1,435 millimeters. And that's also an open standard that was adopted in 1886, so that's over 100 years old. And there's over 720,000 kilometers of this standard compliant interface installed all over the world. And this allows hundreds of vendors all over the world to build compatible equipment. So if you're a train manufacturer, you're going to adopt the standard because otherwise you're going to have a hard time selling your products. If you build a new train track, you're probably going to use the standard because otherwise you're going to have a hard time sourcing the equipment to drive on your train track. And so this really benefits both sides there. Now what is interesting, it's still used to this day, despite there were many proposals to build seemingly technically superior solutions, right? There has been so many maglev train proposals or Hyperloop or all these kind of seemingly technically way superior solutions to this problem. But still, it's still way easier to just use the standard, right? You can build a new maglev train track between two cities, but it's probably better if you just improve on the standard and just make sure that your regular train tracks that adopt the train track standard are just maybe better vibration isolated or a bit more robust, a bit more durable. And that's what really happens. So you can take a train from 1886 and place it on a modern piece of rail track and it will work just fine. Or you can take a modern train and put it onto a 100-year-old train track and it will work just fine. But both of them are actually quite different. So if you compare the train from today to the train from 100 years ago, it's a lot different, and for the tracks as well. So the standards have really allowed the two industries, so the one that builds the tracks as well as the ones that actually builds the equipment, to evolve on their own and to really make their product into a much better solution. And what I found recently, actually a week ago, is quite funny. There's this company in Europe that is claiming they can build maglev on standard compliant rails. So basically they say we can take existing rails and make them into magnetic levitation technology things, because the pressure to adopt the standard is so high that companies are looking into solutions to somehow make it still compatible with all the other trains, but still bring in some sort of fancy technology. Yeah, so in the drone world, we're not quite there yet. I would say there's two main ways you can integrate the drone right now. And I would say one of them is called, I call a shallow integration. Whereas the other one I call a more deeper integration. So let's start with the shallow integration. This is basically when you adopt mainly the Pixhawk connector standard here, and maybe the Pixhawk Payload bus standard. So you can buy an off-the-shelf component that includes all of these parts here, maybe even includes the Pixhawk Autopilot bus. And these components, we all know. It's, for example, the Holy Bro Pixhawk 4, this guy here, or it's any of the newer versions of it. It's the Auterion Skynode, it's the same thing. It's basically a hardware component you can buy. You can put it on a drone, you plug in your motors. You have, in the case of the Skynode, you also have the Autopilot bus electrical connection. You have the connector standard, you put on your external sensors, and you're good to go. I call this a shallow integration because basically the whole avionics on your vehicle is sourced from external, is sourced from an off-the-shelf component that you put on. Sort of a deeper integration is when you roll your own baseboard. So you say, I still want to be standards compliant, that's out of the question, but I don't want to just put a flight controller I buy on eBay on it. I actually want to make a nicely tight integrated baseboard that fits well with my mechanical design, that fits well with I want to do my own electrical design on it, I want to do my own battery bay and all that kind of stuff. And then it's the Autopilot bus standard that you would adopt rather than the connector standard, really. So you would build your own baseboard where you put in the Pixhawk Autopilot bus standard, and then you probably still buy an off-the-shelf component for the FMU. You can stick that on, but on the baseboard, you're completely free, right? So you probably would integrate the ESCs onto the same board. Then you have maybe your mission computer. You would have probably your radio module also on the same board, so that you can make all a lot smaller and a lot better integrated into your overall mechanical design. So there's an example for a deep integration, which is a project we've done with FreeFly from Auterion, and it's the FreeFly Astro. Maybe some of you know it. It's a deep integration. So they started off with Auterion Skynode as sort of a shallow prototype start. And then they took the reference design of Skynode and just basically copy-pasted the electronics onto their own baseboard and added their own things. So they have their own ESCs, they have some of their own hardware on there as well. And they adopted the Pixhawk Autopilot bus on the bottom, so you can plug in different payloads. It runs PX4, so you could pretty much run upstream on it. It's not advised. And yeah, so that's really an example of a deep integration with a custom baseboard. And it's a really nice product. So it shows that you can use Pixhawk and PX4 and all these open source things and still be standards compliant. You can be standard compliant, but still build a nicely, tightly integrated product that really meets consumer demands. Yeah. Has smart batteries and all that stuff. Cool. All right, any questions so far on this? Yeah, go ahead.
So the radio standard,
Mm-hmm.
can you go back there again? Is that telemetry or does it include RC? And do you have any comments as to why, if it doesn't include RC, why we haven't standardized that? Because I just spent a lot of time doing that on the driver.
Yeah, I mean, S-Bus is just one pin, really. Yeah.
Proprietary protocol, right?
It's basically UART, but with inverted polarities, right? Yeah, so it is standard as far as I know, yeah. But why did you have to change? I think it's in PX4, right? There's an S-Bus driver in there. But didn't it work, or?
Oh, it works, but it's, it's not, is it a standard? That's what I'm asking. Is that part of the, because I didn't see it in the doc.
It's not Pixhawk standard I'm not sure how much of a standard it is outside of Pixhawk, but it's something that was there before. Let's put it that way. It was something that was there before the drone world even, right? It was there for like RC planes and stuff. So it's not a Pixhawk standard. I think it's a bit like PWM controls. It's something that just evolved out of the hobbyist RC space and is somewhat the pseudo standard by now. But it's not like, it's not in the Pixhawk docs, that's for sure, yeah.
PX4s all have that same RC input, and it's, the drivers and receivers are just UART driver receivers.
Yes, yeah. Yeah, I think it just uses the GPIO on PX4, and it just doesn't, yeah.
Just online, just real quick, on the processor connector,
Mm-hmm.
there is Ethernet, and on the payload interface is Ethernet.
Yes, yeah.
But they didn't adopt it on the connector standard. Is that what you're saying?
Well, Ethernet is there, right? So Ethernet you have on the radio interface standard. Right, I mean, so, yes, yeah.
I didn't see it on the connector standard.
Right, yeah, no, yeah, you're right, you're absolutely right about that.
Internally, they just didn't bring it to the baseboard. Do you know why?
I think it just predates Ethernet being common on the, so the connector standard just predates the, it comes from the time when we had the F4, which didn't have Ethernet, I think. And it just hasn't been updated there. Yeah. And yeah, so they have different connectors, right? So the radio interface standard is a different physical connector than the payload bus standard is also do I have it? No. It's also a different electrical connector than the connector standard. So the connector standard is all about the JST plastic connectors, whereas here we have these higher density connectors that are defined here. So I think it's just not defined for the JST connectors at this point. Yeah. So for the radio interface standard, I think this one doesn't include S-Bus as far as I know, but I'm not entirely sure. I can have a look later on. It's mostly for telemetry radios these days. Well, or high bandwidth data link even, so for like video streaming and stuff that you would have on it. Yeah. Cool. Any other questions? Cool. Yeah. So let's go with some driver examples that I've been preparing. When would you actually need to write the custom drivers? So I've been talking about all these standards all along, and you're like, well, I'll just adopt the standard and no need to write drivers. And yeah, you're right. If you do, then there's no need to write drivers. There are some situations where you would need to write your own driver. Let's say if you're a hardware vendor, you have your own chip, you have your own external component, and you want to sell that, then you probably want to write the driver for it. Or if this is a very new chip or something that just hasn't been integrated before. Yeah, some standards are really just about electrical and mechanical connections, like the connector standard or the payload standard. So in that case, you still need to write a driver if you have hardware that's not supported. Chances are very high, though, that whatever you're trying to do probably has a driver. So I had a pretty hard time finding any components that I can do an example for this workshop that didn't actually have a driver in 3 already. It would have been a bit useless to write a driver that's already there. So yeah, I found one, which is an LED driver, some, I think Texas Instruments, RGB LED driver. It's an I2C device. And yeah, so I just really soldered on. I made it standard compatible, right? So I took this thing, soldered on the cable, which has a JST GH connector on this side. And now we can plug it into a Pixhawk. And that's what I did. So here, it's now plugged into the I2C port, a standard port on the Pixhawk. And it's not doing anything, so we need to write a driver. All right, let's get going. Drivers in PX4 are actually quite simple. So you probably know that we have YORB, and YORB is this pub/sub system, so you can publish data and subscribe to data. And all the internal communication within PX4 runs over this YORB pub/sub system, right? So drivers either just consume data on a certain topic and use that to drive some hardware, or if it's a sensor driver, then you read out some metric from your sensor and you just publish it over the YORB to be consumed by other modules. So really, it's just writing a module that consumes the data and then does some physical action. Or you measure some physical action and you send out the data over YORB. That's really all it is. So in our case, we need to listen to a YORB message, in that case, LED control, which in our driver, we then parse that and we think, oh, what does that mean for our device? What kind of commands do we need to send to our device to execute what this message means? And then we send that over a physical interface to our device. Yeah, so in that case, it's an I2C device. So the easiest way to start with any new driver in PX4 is you just look at other drivers, right? So for an LED driver, there's already, I think, 2 different chips that are well supported within PX4. So if you look at the structure of these drivers, you get a very good idea on how it should be done. This is basically the class inheritance structure that for any I2C device that you have in PX4. And it has basically 2 parents. So one of them is device I2C, and the other one is I2C SPI driver, the template of this class here. And The left part here is really about the hardware. So it's actually about transferring bytes over the I2C bus. Whereas the right-hand part here is more about the life cycle management of the driver. So the driver that has a start, it has an end, it gets scheduled in the work queue. So that's this part here. This part here is really about devices. It's really about how do I modify bits on the wire. Also, there's the option to implement a character device interface. So you can make your driver appear as a character device in NATEX, so that you have /def, and then you have your device node there. Let's say if you have a display over I2C, you could make it such that when you do echo hello world pipe /def my device, it would pop up on the device. Right? That was more used in the past. It's mostly has been abandoned by now because of performance. So these character devices always they require these I/O control calls over the operating system, and for performance, it's not that great. So that's why this mostly is no longer done. So when you go on NATEX and do ls/def, you don't see all that many devices there. So on this side here, we have, so it inherits from work item. A work item is a thing that can be scheduled on the work queue. And the work queue is this execution context where it's basically a synchronized queue of things it does. So it does this first, and it does this, and it does this, and then it's this. And the whole queue gets scheduled with all the other queues. So it's not that all the modules we have in PX4 actually are just scheduled randomly from the NATEX scheduler. Most of them actually sit in these work queues, and the work queues themselves then get scheduled by NATEX. But the order of execution within the work queue is fixed. It's just one module after the other, really. So our driver will run in the work queue, of course. Cool. So next step, we go onto the datasheet of the thing, and we find a register map, which is massive, has a lot of features, the thing, which we won't use. And the code is on GitHub, but let's write it first. Well, write it. I have it written, of course. I cheated here. So let's get started. So this is really, if you look at the file system here, you have in PX4, you have the source folders, then there's the drivers directory. And here you have sort of the classes of drivers. You have barometer, you have GPS drivers, hygrometer drivers, IMU drivers. We want to do a LED, a light driver, so ours goes into light, right? Then we create a new folder for our device. I just followed the one from this chip here, so it's another LED driver chip, and I copied that here. Then you do a CMake lists file to add your module to the CMake. And you can also add a kconfig file to make it menu configurable. So when you do make menu config, then you get the option to include the driver into your build or to not include it in your build. In that case, I added it. It's pretty easy. You just copy it from another driver and modify it to your taste if you want to do that yourself. The CMake is also, we use in PX4 our own macro to add module. So CMake would have their own add module, but we use the slightly modified version. So also, you basically find in other modules how you would use those. It's pretty straightforward. You just give it a module name, main function it should call as soon as you launch it. All source files you want to include, plus all dependent libraries that you need to include. That is just for the linker that depends on it, which libraries the linker should link against your stuff. And then for the good stuff, you start your own CPP file here. And as I said, you write your class. You inherit from these two interfaces, so the device I2C interface and the device and the I2C SPI driver interface. Now these interfaces give you a certain set of functions that you need to override. And this is really the PX4 API for drivers, for SPI and I2C drivers that you need to implement for your device, right? So you need to do a constructor, of course, destructor. There's this print usage function you need to implement. That's basically the function that prints onto the terminal how you use your driver. So something like list of arguments and what they do. A probe function. The probe function shall test if the device that you're trying to start is on the bus. So PX4 will try to start your driver, which then should start the device and initialize it and all that, and probe basically should return if the device you're requesting is actually present on the bus. The init function then gets called after probing. So when probe returns yes, that device is here, then the init function gets called. If that one succeeds, then the run implementation function will get called indefinitely, basically, by PX4. It will just get called and called and called and called until the destructor is called in the end. In the run implementation function, you're then free to do what you need to do. So in our case, what we'll do in the run implementation function, we'll pull the LED topic, and we'll see if there's any LED we need to turn on, turn off, and anything we need to do there. Does that make sense? Cool. All right, let's get started. I tagged every step along the way, so I think I can just do a git check at step 2, right? And yes, here we go. So in our case, we're actually not going to listen directly to the LED controls topic, because the LED controls topic contains things like, I want your LED to breathe on and on, I want your LED to blink, I want your LED to do all kinds of crazy patterns that you don't really want to re-implement yourself. So you don't really want to implement the state machine for breathing on and off an LED and these kind of things. So there's a library in PX4 that does this job for you. And that library is called LED controller library. So if you go into LED controller library, you see that it does things like checking if breathing is enabled for that LED. It does all these things, right? It does all these things for you, and it's actually a fairly involved library. But what you also see here, it actually subscribes then to the LED control topic. So it subscribes to the Europe topic for LED control. And it basically does most of the work for us already. So this LED controller class subscribes to the topic, reads in new data, checks which color at which intensity should be running. So it checks which LED should be which color at which intensity and gives us that back. And then all we have to do is take that color and intensity for this moment in time and send it to our controller. So this is handy. So we just instantiate this library here and we're good to go. Now we don't have to do that. If you care about doing this yourself, free to go. This is not something that is required. But in our case, it makes it much easier. Cool. Let's go further. Now, next step. If you write any driver for any device, chances are somebody has written already a driver for it for another operating system or another project. Good candidates are things like Arduino or some other open source driver framework you might find out there. And a lot of the code you find in these projects, you can pretty much just copy over. And a prime example for that are all the constants. So if we look at the data sheet here, you see there's a massive register bank here. So this device has a big register bank of all kinds of registers they can use to control features of the device. And the first thing generally you do when you write a new driver is you list out all these, you write aliases for all these register addresses and all these bit fields, right? And I didn't do that myself. I just went on the internet and looked for LP55231 driver and found one for Arduino and I just copied it over because why would you redo that work, right? And so here we are. So this is just straight up copied from the data sheet or from another driver, which copied it from the data sheet. So it's just a list of all the register in that device. And you just copy it in here. So that's all I did here. Right. Let's continue. First step, what do we do? Right. Cool. Now, before I mentioned that we're inheriting from two interfaces. So one of them is the device I2C, this one here. And this one gives you the low-level I2C functionality out of the box. So PX4 already interfaces with the NATX I2C driver. It does all this stuff for you. It abstracts away the actual microcontroller I2C device, hardware device from you. So you don't have to care about it anymore. And the API to this I2C hardware device on the microcontroller is this function, is this device I2C function. So when you run on, let's say, an STM32, you can use device I2C and do I2C stuff. If you run on a NXP K66, you can do the same thing. And it just works because the API is the same, but maybe the underlying hardware implementation of the I2C device is quite a bit different. Now, this class provides you with a function that you can use, and that function is called transfer. This function is quite low level, right? It just executes an I2C transfer. So it sends some data, receives some data. And the API here is you give it a pointer to the data. You tell him how's the size of that data that you're writing. And you tell him where to store the data that you're going to read and how many bytes you're going to read after that. And this function does that. This is handy for a lot of cases. So maybe you have I2C devices that expect you to write 100 kilobytes as one block, or maybe you have an I2C device that just requires you to write 1 byte at a time and then read another byte. So with this transfer function, you can use all these, you can basically build all these cases quite easily. In our case, our device is very simple, which is nice. So our device only ever requires us to write a single byte to a single address and to read 1 byte from a single address. So we can abstract away this transfer function into a write and a read function. And our write and read functions are quite simple because we only ever want to write to a single address, a single byte to a single address, and an address is just 1 byte in our case, because there's only 255 registers. So we have one address, we have 1 byte, so 1 address, 1 value, which makes 2 bytes. We put in an array, we send them over, and we don't need to read anything back. We just send off 2 bytes. Same for read. Read only requires us to give an address and 1 byte where we read it back. So we tell them we tell it the address. The address is 1 byte, so there's a 1 here. And this is casted to a pointer where to read the value back from here. So we can just have a handy write and read function that just does this for you, so quite easy. So let's continue. Cool. So we can consult the datasheet, and we see there's a reset register. So we implement the reset function that does nothing else than write to the reset register. So now we've implemented chip reset in our driver. The other one is enable. So we again consult the datasheet. We see that there's certain registers you need to set. You can enable and disable certain features on the chip. And in our case, we need to, we basically need to do this. So these are some magic values I plugged in here. You can also build them up using the constant so that you can more easily see what kind of features you're about to enable on the chip. But yeah, in that case, I just put in some magic constants. So we'll write those to magic constants, which will enable the chip for us to go. Okay, let's continue. Cool, now probing. Probing should check if the chip is present. And that's sometimes more difficult than you think. So a lot of I2C devices have a register that you can read that will tell you a constant. So you see in the datasheet, this register always contains this value, and there's some sort of manufacturer ID or a chip ID or something like that, right? So you can read that register and it will tell you a chip ID. And if you have that, you just write the probe function in a way that you read this register. If the chip ID matches, you say, yeah, it's probably that chip, and you're good to go. In our case, our chip doesn't do that. But what you then can do is you basically look at the register map and you see some register and look at their reset values. And if you find some that are very characteristic for this device, then you can use those. So you can say, well, if I read those certain registers and they give me back these values, then it's a high likelihood that it's actually this chip on the bus. In PX4, we currently rely way too much on this probe function. So there's, if you put in your startup script that you start a certain driver, it will use the probe function to check if the device is there. And if it's not there, it will just not start, but it's not treated as error or anything, except for sensors if you have calibration. But where we want to go to is basically that you define a static set of sensors that you expect to be present on your device. And then the probe function is not really an identification thing anymore. It's just really to check if something is present. So it's not, we kind of abuse it as an identification on let's figure out what's on the bus kind of way, even though, yeah, for I2C, it's not really that well defined in that case. So what we do here, I just look at basically two registers that should have a fairly characteristic value for this chip. So one is the on-off. So we check a register that controls if certain LEDs are turned off or on. And when you reset the chip, everything should be turned on, right? So this should be 0xFF. And then we check another one, and that's current control. And this register controls how much current you want to send to the LEDs. And that one initializes with this value here. So we just check that one, and if that matches, then it's a high likelihood that we're actually talking to the chip we're intending to talk to. Doesn't guarantee it though, which is, as I said, is not always great. Yeah.
What is the return? It looks like you're returning AF.
Where?
And the return, it's returning AF, but what is the probe actually expecting?
The probe is expected to return 0 when there's no error.
Minus a 0 as a return.
So that one would be an error, right?
Yeah, but look at your code at the bottom. You return the read.
The return. And ret would be 0 if the read was successful. Right, so it writes it into this current control. Yes, so if it's successful, if the read is successful, this one will be 0. And if the read failed, well, then probably also this would fail, but if this would magically not fail, then at least this would tell it that it failed. Yeah.
0 is okay.
0 is okay, yeah. All right, so yeah, almost done. Next, the init function. So in the init function, we first call the super, so the I2C class's init function, which sets up the I2C driver on Nantex if it's not already done so. Then we reset our chip, we enable our chip, and then from the other interface, so that's the work queue interface from our driver, we say schedule now, which means consider us from now on in the scheduling of the work queue, so that our run implementation function will be called periodically after that. Cool. Where are we now? That was that. Right, and then, so the last sort of low-level function we need to do is this set channel PWM. So we basically get from the LED controller now which LED should be at which brightness. So we will need to write a function to actually send this value to our device. And in our device, it's just, there's a register PWM for the PWM value of a certain LED. And we just set the nth channel PWM channel to the value we get. And this is just a simple write. So that's all there is to do. Okay, and now to the actual control part. So this, as I said before, this LED controller class from PX4 subscribes to the LED control topic. And this is just a speciality of this class, that it gives you two values. It basically gives you an integer, an 8-bit integer, which contains the brightness, and then it contains an enumeration of the color of the LED that should be running. So it gives you, oh, right now the LED should be 20 out of 255 at the color purple. And then your driver has to make sure that will happen, right? So in our case, that means assigning the brightness to the right channel. So we have a red channel, a green channel, and a blue channel. And in the case of purple, we say it's half red and half blue. So half the brightness goes in red and half the brightness goes in blue. If you have white, 1/3 of the brightness goes onto each channel. And then in the end, we use the setChannel PWM function we just implemented before, which then will write that value onto the PWM of the chip. And then we put the schedule delayed in. So this is again from the interface from the work queue interface that we're inheriting from. So this function tells the work queue that we do not need to be scheduled right away after that, because it's not like a high frequency kind of thing. It's okay to be 30 milliseconds delay, because that's what human perception is on an LED like that, right? You don't need to schedule it that quickly. So we just put that, and also there's a constant you can use from LED controller, or a configurable value from LED controller you can use for that. Okay, then yeah, so that's our driver basically. The last thing you will have to add is the main function. The main function can use another library that's provided as bus CLI arguments, which is a class that's specifically for I2C SPI drivers, which does already parse certain common CLI arguments like the I2C address, the rate you want to run at, which bus you want to run on, and that's quite handy. So you can just use that and then just pass it on to your module. So this module start and module stop functions are also functions that are in the base classes we inherited from. And they will configure the NATX I2C device to use the right addresses. So that when we use the transfer function, we're already talking to the right device. So this is a part you can really just copy over. All right, should we try it? Let's try it. So we can just do make Pix4 FMU v5 upload. And we're failing. Because I'm sitting at a tag, it doesn't like that. Right. Git tag -minus delete. That's done. Right. There we go. Yeah, that's a demo effect. Ha, worked. Let's see. Forget it to flash. Doesn't want to go into the bootloader. Let's replug this guy. There we go. All right, fingers crossed. There we go. Working LED. And now it should be green then after a while. Is SAH enabled, I think, on the thing? Yep, there we go. Now we're green. Now we're ready to fly. Well, an SAH. Cool. Yeah, so if you want to play around with the code, it's a slightly better version of the code than the one that I just presented now. Then you can go in here So the one I put, so this is an upstream code that also allows you to control all 3 LEDs. So the LED controller class actually gives you a value for all 3 LEDs, and with that one it controls all 3. It's also a bit nicer written and all, but the concept's exactly the same. So you can check that out if you want to. I might do a PR and we might try to get it into upstream, but I mean there's not really a drone right now that needs this driver. Cool, all right. Yeah, any questions? Feel free about standards or drivers or anything. Yeah.
Very good reference for serial, like a binary protocol driver, right?
Yeah, so the GPS drivers are all serial drivers essentially. You can have a look in those. Yeah, that'd be a good starting point. What else is there? Yeah, it's the only real serial device we have. There's the PX4 I/O, which is connected over a serial, but that one uses its own proprietary little driver that goes directly onto the STM32 and goes around NATEX. So don't look into that. That's something you want to get rid of. Yeah.
So the same question for yourself.
Mm-hmm.
What would you recommend you start with?
Sorry, again?
For auto Ethernet,
For Ethernet. Well, so far on Ethernet, we just use the IP stack, really. And there you just do sockets, really. Yeah, so in NATEX, you can just open UDP sockets or TCP sockets and go with that. So that's the only thing we've so far done over Ethernet. Yeah, and there I don't think there's any drivers for any specific kind of modules yet in PX4, but the structure would be similar. So you would add a driver in the drivers folder, and that driver in the initialization would then try to open a socket and like negotiate some specific.
is the 5 set for the module like these? What kind? Because auto Ethernet 5
Which track? Sorry.
the auto Ethernet 5s are different for different 5s.
Mm-hmm.
So do you know if there's a standard for that 5 or if the driver for those different 5s?
I mean, that's all done on NATEX level, really. You would have the NATEX driver and then just open, it would just be a network interface on NATEX that you would then use. I think that would more go into board support then. I haven't looked into that, so that's more a question for David to train in the end, I think. But in general, I don't know how good the drivers are. So on the F7, we're using the Ethernet driver, and that seems to be working, but we had some pretty big problems at the beginning. So we had some hard faults and stuff. Yeah, so it's really just a question of how good the drivers are in NATEX for those things. But yeah, I would recommend just to use the socket interface for anything Ethernet. Actually, it's the same a little bit for CAN as well. So I think the UAV CAN now goes into socket CAN, which just opens a socket in NATEX. But other CAN devices go directly onto the device. So yeah, there it's a bit. We could discuss whatever device you want to integrate, and probably in the dev call be a good format to discuss that. Right? Okay. Any other questions? Cool. All right, then thank you all, and enjoy the rest of the summit.